Hi, I'm Robert. And like, everything set? Yeah. Like 1.5 years ago, I had the great task of graduating. I was in a master's program at the University of Oldenburg, which is in Lower Saxony in Germany. We have really nice weather. As you can see, I'm pretty not used to sun. So this is why I got my sunburn here in the first day. And yeah, I had pretty much a free choice of what I wanted to do. And I really liked the languages, and I had to look at D, and I really liked it. And so I thought to myself, what to do with it? So I had to do something new and something like creative. And I thought, why not build a compiler? So I sat down and had like, basically wrote down what I wanted to do. And I come up with a few things that I thought was like worth thinking about again. So yeah, and this is what I want to talk about today. So at first I'm going to give a short introduction about what I've done and where I'm coming from and where I got my ideas. And then I want to talk about how I changed the structure of a compiler, or like more or less the control flow of the compiler. And yeah, I built in a few things like multi-threaded Lexer Parser communication and some caching. And then I thought, why don't I write a parser and Lexer generator to make use of it and to have a faster, like changing the language, recompiling stuff, workflow. And then I'm going to give a small conclusion on how it's turned out to be. So as I came to the topic, I've pretty much found out that since Grace Hopper, the woman who invented the COBOL compiler and the predecessor to that, which name I always forget, compilers haven't really changed that much. So there's basically still a parser who's asking the lex of the token, and then at the end there's some code emitted or even some assembler emitted, and yeah, the program runs and this is done. But the hardware has changed enormously. I mean, since then we have 10,000, the amount of RAM has grown by a factor of 10,000. The CPU power has grown on a factor of a couple of thousand. Networks are available and are extremely fast. And hard disks are pretty much unlimited. And back then, you were happy if you had like a couple of bytes of memory. So hardware has changed a lot. And the compiler construction or the way it works hasn't really changed that much. So what I thought, why not adapt the compiler to this change? And also what I wanted to do is learn pretty much everything there were. So I had a basic programming course, but that didn't go into how to construct a vector, how to construct a map. And it didn't go on how to write printf and how to write a string buffer, which is pretty much a vector, but if you think about it. But yeah, all this stuff was pretty not, I know basically what it would do and how it should do it in my understanding, but I didn't really know. So I thought, why not learn this while writing a compiler, which was, like, in hindsight, a pretty stupid idea because I only had half a year to do it. But anyway, I sat down, opened a file, and started hacking. And of course, I wanted to graduate, so I had to like write a paper on what I've done. And yeah, so how did I want to adapt the compiler to the new hardware on the hardware capabilities I had? The first thing I noticed, I have multiple CPUs, or multiple cores, and maybe even multiple CPUs and hyperthreading and all this good stuff. And I also have pretty much unlimited amount of RAMs. So yeah, maybe I should use caching to speed things up, because this is basically what you do. You would compute a result and try to reuse it as often as you can, because pulling it from RAM is pretty much most of the time more efficient than computing it again and then using it. And I also thought, well, I had a network and my friend had a laptop running and there was the server of the university, and why not use this as well for compiling stuff? I mean, basically the CPUs are bored all the time. So once in a while, when I want to compile things, I want it to be really fast. And the idea was, why not drop it there and let them compile some stuff and let them send me the object back. So, and to not have to write the Lexer by hand, which I thought was stupid then, I thought, why not create a Lexer generator? Because most textbook I wrote about this was, well, you can use a Lexer generator and it's going to generate your Lexer. And I thought, well, this should be nice. And the theory behind Lexer generator isn't that complicated. So why not implement it myself and have a file description file of the language I actually understand. And yeah, this led me to the Parser generator, which basically took the same path as I thought, well, there are generators for parsers, and at that point, there wasn't any good one for D, which I was comfortable using, and I actually wanted to understand this to write some text about that my professor can read and give me a good grade for it. So I thought, well, let's generate a parser. Let's write a parser generator, which generates me a parser in D, which I then can use to create a compiler which does everything differently. And what I found out pretty early is that I needed a container. Well, of course, there's the append or the array and the dictionary, but I really wanted really know what I was doing, and I liked pretty much the vector of C++. This was the data structure I was finding all over my source. So I thought, well, if I'm at it, why not write a vector? So I opened, again, the terminal, created a directory, and started a vector. And this led to some interesting stuff. For instance, implementing an RB tree isn't as simple as you think. There are many variations on how to do this stuff, and it's also interesting to use this kind of data structure in different things like a set and a map and a multi-map. And even if you combine a map and a set to get something similar to a multi-map, but with set properties, which I call map set. And actually, this map set is pretty much what you have if you try to save the transition graph of a Lexer. It's pretty much a map set. So you have an input or a state, which is like the key value, and you have some corresponding following state, which is a set. And this must be unique for every character you put in it. So I created a map set because I thought the code was duplicating all over my Lexer generator, put it out, making the map set, and yeah, this was pretty easy doing in D because there was not many headers or no headers I had to rearrange, and yeah. So these were the ideas I had 1.5 years ago, I think in the beginning of 2012. So then I started hacking. And before I started this, I thought about how should the compiler look which takes advantage of all the hardware capabilities we have. And I came up with this representation of the control flow. So just for definition type, so that you know what I'm talking about, we have phases, which are marked by the dotted blue lines. We have processes, which are the dotted red lines. We have data structures, which are used to exchange data, which are the round circles. And we have threads, which are the blocks. And so what I thought, well, the Lexer can just put all the tokens he gets from the file in a buffer, and the parser can come and just take whatever he can get and create the AST and the symbol table from then. And after that, we do all the semantic analysis in a different thread and just blow it to the AST and let them run over it. And if they don't complain, then we just gonna generate the code at the end. And the first part, the Lexer parser communication, if you really think about it, is just the classical consumer-producer problem. We have the producer, which is the Lexer. He generates the tokens from the file. And we have the consumer, which is the parser, which just reads the input from the Lexer and does something with it. And historically, and which is pretty much true from whatever I found, I looked at the DMD source and I looked at the Clang and whatever DCC. What it's done is that the parser asks the Lexer for the tokens one by one. You step it really. And what this leads to is interruptive use of the I/O device. And most of the time today, we still have hard disks, and they have some kind of head which is moving around the spindles. And if the operating system thinks there's another program which needs a file, and currently our compiler doesn't need the hard disk, this head might move away. And as this is really a mechanical device, this takes time, really time, milliseconds even if in bad cases seconds. And this is bad, we don't want this. And to work against this, I thought, why not have a thread pulling as much I/O as we can at any given time and generating as much tokens as he basically can, up to a limit where we say the buffer is full, basically to not have to run into, to reallocate the buffer structure all over the place again. And yeah, there we are basically fighting the operating system to give us the hard disk like in a mutual way. And yeah, as I said, the Lexer now generates, or in my compiler, the Lexer generate the token in a separate thread. And to limit the amount of synchronization we have to do, the parser actually takes as much tokens as he can find in the buffer at any given time whenever he tries to get a new token. So he basically holds another buffer where he just mem copies the contents of, which is basically an array, into his array. Clears the buffer, and then the Lexer can run again and dump the buffer full. And this actually gives some performance improvements. The first file is pretty small, just 3 lines, but as you can, there you can actually see that the synchronization is a penalty to what you have. So the yellow lines is the multi-threaded approach, and the green lines is the single-threaded approach. The x-axis is the buffer size, and this is the time in seconds. So of course the Lexer is extremely bad, but because it's generated and the table gap becomes very big, it's not nearly as fast as the Lexer employed by the decompiler, but still it's just like to get an idea of what you can gain. So, but as the files grow bigger, for instance, the one in the right corner has like 27 lines, and this goes up to 1,000, you can see that the yellow lines, or the multi-threaded approach, gains some speed over the single-threaded approach. And this is basically what I aim for, to make the parser-Lexer communication faster. And yeah, as you can see, this worked to some degree. Where the files get really big, like 1,000 lines, the results get a bit more inconclusive. This is probably because the garbage collection also runs into it, because the buffer is grown to some amount, but not to like, it's limited somewhere, so the garbage collection comes in. And also there I create the AST internally, and this is done on the heap. So there the garbage collection does also some things into it, I think. But yeah, I think the dividing the Lexer and the parser into separate things is basically a good idea to get some performance out of multi-threading. So the other thing I thought is the semantic analysis basically just checks if your program is doing everything correctly in the sense which cannot be tested in the grammar of the language. So for instance, that there's a return statement. It's extremely hard to test in a context-free grammar. So that there comes some handy little function into it, which just checks if like the return statement is reached, or in any case it's reached. And it does this by looking at the abstract syntax tree and the symbol table. And this analysis shouldn't modify your data. And these tests can be independent of each other, because checking if the function does return something, and if the constantness of the arguments isn't violated, are separate, at least in the sense if you think about them. So I took the approach of thinking of writing the functions independent, just writing a function which gets an AST node and checks whatever it has to check, and run them in parallel, because basically, as I said earlier, or as I stated earlier, these functions are independent of each other. So why not run them in parallel? I mean, we have 16 whatever cores. This could speed things up. And the good thing is, as we know it shouldn't modify any data, we can do it without locking. So all these threads just run on the data, don't modify anything, just look into it and say, you're doing it good, you're doing not so good. And this gives us some extremely interesting results. The green, just so you can see it, the green lines is representing one thread approach, which is basically like the case we have it right now, that there's one thread running through the AST and checking all the problems we have, or the checks we have to do. The red one is the two-thread approach, which goes up to the 16-thread approach with the yellow line. And again, we run this on the 4 separate files. I mentioned, from a very small file of 3 lines up to a file of 1,000 lines. And to simulate a real semantic analysis, because at some point I pretty much ran out of time, I just multiplexed the few tests I had, so that I can have up to 60 jobs to get a meaningful result of whether or not running these tests in separate thread actually gives us a speed up. And if you look at the extreme, like the 1,000-line files, you can actually see this was run on the 4-core machine. That the 1-thread approach is slower than the 2-thread approach, which is also slower than the 4th-thread approach, and so forth. The peaks, again, has something to do with garbage collection or runtime scheduling. I really don't know. I've looked into it for more than a week and couldn't really find out where these peaks came from. And as I said earlier, at the end, I pretty much ran out of time and had to just stay with this. But as you can see, multiplexing the check functions onto multiple thread actually gives you something. And basically also forces you to write more clean code by just having one function checking only one thing. And yeah, the third modification I thought about was source files are pretty much not independent of each other. So if you generate the dependency tree of any program you have, you will find that 1 or 2 or maybe more files are like imported or included a lot of times. So basically you have stdio, which is like imported pretty much in every source file you have. And many of these files don't change over time. For instance, if you like, again, take stdio as an example, you will see that probably over half a year this file doesn't change. And the question is, why do you read it or lex it and parse it every time you try to compile a program which includes this file? Why not have it cached? I mean, yeah. And what I also thought, when I do caching, why not use the cache data for like speeding up the distribution of work in the network and vice versa? So for instance, if I have some machine somewhere in the back of the office compiling stuff and I ask it again for AST for SDIO or SDIO algorithms or whatever, why shouldn't it just return this result? I mean, this pretty much multiplies the amount of cache I have by the number of machines I can use. So again, this like is a combination of 2 features, the distribution and the caching. And the next thing I thought about was on which levels is caching useful. The levels that came to mind pretty fast were the file level. For instance, I just could hold a char buffer in memory and then just lex it again, create the AST, maybe some intermediate code and return it. Or I could also cache the token levels, because then tokens are implemented in my implementation as structs, which is basically just memory again, and I can hold it in an array, and then just return and point it to this array, and be happy with it. And the next thing is the AST level. And this is where it gets interesting, because the AST, by its nature, is a tree. And to store trees in memory is a bit more tricky, because if a tree is not uniform, there's not really a way to map it on an array, because memory is in the end just an array, or the other way around. And so I come back. So mapping an array which is not a binary heap or denary heap and not completely filled onto an array is difficult, because you can't do some arithmetic to get the child or the parent for binary trees, like multiplying the index by 2 and adding 0 or 1 to it, depending on what start index you have. But again, I wanted to have this tree flat, so I can just have some memory which I use for cache, and then just dump it in. And if I want to retrieve it, I just get the pointer, do a cast, and be done with it. So I created a way to flatten non-uniform, non-completely filled trees, which I have called linear trees or linear trees. And To consider this, let's just take a look at this like simplified AST. So we have a start symbol, which decals down to a return statement and says some basic types and identifier and whatnot, and basically just builds this nice program into AST. And what I then have are two arrays. I have the array of nodes, and I have an array of child pointers or children pointers. And I have, inside these nodes, I have two members, which basically build up in a slice. And the slice basically starts with the index of the first child, which is basically the pointer of the slice. And I have a number of children I store, which is the length of the slice. So starting at the S symbol, I see that I have the index of the first child is 0, and the number of children I have is 1. So what I do then is to look into the children array and see, like, this leads me to the first index of the array, or to the 0th index of the array, and this tells me that the actual first child is located at index 1 in the node array, which brings me here. And again, I look into the the children index array, because I want to go to the next one, which brings me here. And as I know from this number, I know that I only have one child, and because of this mapping, I know it's at index 2. So as you can see, we go from S to decal-def, and where it gets more interesting is if we have a slice which is larger than 1, because then the number of children we have is greater than 1. And this is a point at the declarator. So as you can see, we have 3 children starting at the index of 3, which is here, and the children indexes are 4, 6, and 8. And for instance, if we want to go to the decal-def, which leads to the return statement in the end, we just take a look. Where was I? In the declarator index 3. 1, 2, 3. Number 8 leads me to the decal-def, and we are at the right side of the tree, which leads to the end. And this is pretty much, these are arrays, and so they are easily stored in a consistent chunk of memory. And so we have a non-uniform, non-completely built tree in memory, or in an array, or in 2 arrays, which is pretty much what you wanted to have to store it in as in cache data. And of course, I had to benchmark this to see whether or not this has any possibility to compete to the classical heap-based approach. And what you can get from this data, the blue line, or the blue numbers represent the fastest one, is that you pretty much get the overhead of looking in the second array again. This is pretty much the multiplicator of the performance you have. So for, let's say, 1,000 node, the speed is the same. It's just 0 because it's so small. And if you get to 1,000,000, building a tree is highly dependent of the memory management you have, because up to this point, the class-based approach is always faster because it just has to create a small class node and return it. But here it actually has to find a consistent piece of memory to store all the nodes which are implemented as structs in this array. But again, in the traveling time, you can see that the class-based approach is always faster, and always by the factor of 2 pretty much, because you don't have to look in the second array to find where your children live in the array. So, but again, this time is a millisecond, and I think that the caching gain you get by, the speed gain you get by caching pretty much outweigh the re-lexing and re-reading of the file. So the next thing is, as I said earlier, while developing, most of your CPU is just idle. I mean, if you run some text editor, you're basically not using this much CPU power. Maybe you have some email client in the back, but basically if you look at your CPU time, it's just like idling around. And this multiplies by the workstations in the department. For instance, I bet at Facebook, the average CPU time or the average CPU usage is pretty low, considering all machines running all day in all offices. So why not use this? And if you take a look at the speed of the networks in relation to the size of source files we have, networks are extremely fast. I mean, if you have a gigabit network, sending a 1 megabyte file basically takes no time at all. It's just there. It probably takes more time to make the connection than actually sending the file. So if you hold the connection, sending the file doesn't really take time. And yeah, and then why not just use all the machines which stand around idling to compile the files which we want to have? So if you have 1,000 files and you have 1,000 machines, why not distribute them to all these machines and then just aggregate the results and write the binary out of it? But to make this happen, the compiler itself has to become a daemon, because there has to be somebody at the other end listening for the jobs to come in. And this basically makes the compiler a daemon, which is just running in the background, listening to some port, waiting for files to compile, and then just asking back, oh, I need this file to compile this because this is imported somewhere else. But if you take this approach even further, you can just infer statically with your build tool that these files are included or imported somewhere. You can just send them in one pack and have the files there to compile. And this is the distribution approach. This is basically disk CC, but on a more compiler-driven approach than the make-driven approach. So I'm a bit fast, I think. And then I actually started to write the Lexer generator, and reading the Dragon book, which was published when I was born, which is quite funny, I think. They introduced the deterministic finite automaton tokenizers, the DFAs, to generate tokens from source. And these use a table-driven approach, so you have a state where you are, and you have input character, and then you can just go to the next state, and so forth, till you find an action on how to return the token you created. And I had to write in the ability to pass in a user-defined error function, because I actually wanted to pass or to lex D. And unfortunately, D does not really fit into the Chomsky 2 hierarchy because of dot token, which is ambiguous if you look at the as an or slice indexing array. Of course, you can say there's a white space in front and the back of it, but this is not true if you look at the source you find. Or you have to do it in a separate stage, and I wanted to have it clear, and therefore I had to write this user-supplied error function capability into it, which can also be used to pre-print error messages on, if you are in the state of parsing a floating point, for instance, and you find an error with it, you can, through this function, say, while parsing a floating point function, you have made this mistake. And this makes this pretty easy. But the biggest problem with this was that the table-driven approach becomes hard if you look at UTF-8 or even UTF-32, because you just don't have ASCII for your indexing. You have a lot more. And by a lot more, I mean a lot more, like 1 million characters compared to, let's say, 127, which is... And what this leads to is a graph, which,
Maybe you can just repeat the question. Could you just shortly elaborate on the dot token thing?
Yeah. So if you write an array the question was why the dot thing is difficult to lex when you difficult to lex with a simple table-driven approach. So you have a look at, while doing a table driver, you have a look at of one token. And the problem is if you use the dot dot in an array slicing operation, for instance, you do a bracket 1 dot 2 bracket. You start lexing a floating point because of the 1 dot. But the second dot says it's an integer and it's a slice operator and then another integer. So there you have the ambiguity of not knowing which path to take. And therefore I had to consult to this error recovery function. Okay, good. So yeah, we were at the problem of UTF-8. And this is just like extremely tiny picture of the DEFA graph I created from a very small part of the D language or the token language. You have a start state over there with 0, which is like done with 0, and you have a couple of states there, and the picture goes on properly to the next building. And Dot had actually problems scaling this to a JPEG image and had to scale it down to 1/10 or 1/15 or whatnot, so you can't even make out where the paths go. And this just to like illustrate how big the actual table will get because you have to put it in a table, and this is basically impossible to store in memory even today with all the memory we have, and there's no way of thinking about caching or whatever. But that's the good thing. We can minimize this table because many states lead to the same following state on the given input. So how the actual Lexer then works is it starts at some state, and it has this transition table, and it has a state mapping and an input mapping. And so if you say you're in state 1, you take a look at state row, and depending on the input and the input mapping, you get to the next state. So for instance, if you're in state 0, and you have an input character of state A, the following state is also state 0. The -1 state represents error states. And this can be minimized because, as you see, the transition table or the columns for state 0 and 1 are the same. So they can be merged. And the same goes for the rows. For instance, these can be merged. And this will lead us to an minimized transition table where you just have to rearrange the state and the input mappings. And this is quite good because you can, if you look at a transition table which comes out of a Lex or of a language which also incorporates UTF-8 characters, say for identifiers and strings, you will find that the table which comes out has basically like the keyword part and then two big parts for the identifier and the string part. So, and these characters are basically just all to the UTF-8 part. So these can be pretty much merged together into one consecutive range, and you basically get ASCII +2. And this, again, is then feasible to use in a traditional table-driven Lexer. You just have to do some rearranging and not that much interesting code to actually do it. And yeah, so the Lexer generator, which I call DEX, which is just Lex with a D in front of it instead of the L, no creative name, was able to pass UTF-8, or what I did was to convert the UTF-8 strings into UTF-32 strings to use the number directly as an index, and then just align to 0. Yeah, and the rest of DEX is pretty much just boring stuff, writing out the table into an array, into a D file, and some boilerplate code and the actual runner. Not that interesting at that point. And this leads us to the Parser generator, which is DARIL, or DLLR, which is a Parser generator for both GLR1 and LRLR1. At first I thought maybe D fits in LRLR1, but unfortunately the grammar which is shown on the website doesn't fit. Walt is laughing, I think you know what I mean. And of course I've taken a very close and very long look at the source of DMD to try to fix the grammar and portions, but I couldn't really get around it to get it into LR1. So I put the G part on over it, which basically just allows you to parse all context-free languages, which are Chomsky 2 languages. And again, this is like a table-driven approach, because the Dragon Book and all the other textbooks on parser generator basically told you if you do a generator, you're probably gonna generate a table. And because GLR1 is ambiguous in its core, the user again had to supply not really an error recovery function, but a function which decided which part or which pass was the pass you wanted. And there you have then you probably just identified the cases where the grammar becomes ambiguous, which is like told to you by the Lexer generator, and then you have to check, or you have to write a function which returns which part you really need. And again, the approach on writing this program is pretty standard. You just read the textbook on how to generate these kind of parse trees and then generate a table from them. Pretty basic stuff, but at that point wasn't present in D. So I thought, well, if I'm on it, why not do this as well? Came about like a 10,000 line program, which is like most of the output is related to fitting the graph or creating output which can be processed by the dot program to squeeze it on a printable page or to print it on a page which I can look at the monitor to debug the grammar I put in. Yep. So this was pretty much what I did in my master thesis, and now I'm going to give a small summary on why these things might be interesting to other people and where are the problems and why D is handy in this regard to do things like this. And yeah, so the first thing I learned, table-driven Unicode lexers are pretty much impossible, because as soon as you look at all the characters, which are like, today there are 1 million and a few other characters defined in Unicode, and you have like, say, 200 states in the token language you're trying to parse, it's basically impossible to do this on a machine in reasonable time. But splitting, so the next time I would do this, I would probably not do it at all, but I would do it in a handwritten fashion, because this is much easier. You wanted to ask a question?
Well, why not just take the characters that are treated as unique by the Lexer as the index? Okay, why not just take the characters that are treated as unique by your Lexer as your indices to the table, and then all the Unicode characters that are effectively identical to your Lexer, treat them as the same index?
Yeah, because you know this at the end of the process. So you can't say while parsing the input file for the Lexer generator that these files or these characters will not appear again at some later token. So you have to generate, basically what you do is you generate a regular expression or a non-deterministic finite state automaton for each token. Then you combine it, and then you run a function over it which combines it and compresses it.
So another question. So I understand the problem is that with the table-driven approach is that you try to treat each individual Unicode characters separately. But since the source code is always treated as Unicode, and I think UTF-8, why not just look at UTF-8 code units instead of code points? So then you only need 256 characters, which is basically ASCII.
This is a good question. I think this is yeah, this might be possible, but you have to properly reinvent the input language for this, because you write the input language also in UTF-8 and then parse it in D. And in this case, you get non-printable characters. So for instance, like the 128 is probably not printable in UTF-8, but you have to input it to say that this leads to some character input. But yeah, of course, you can, if you write the input in the way that you just define the number you put in, you probably can do this.
One reason not to do is you get a lot of more transitions.
Yeah.
Like you have, you're duplicating your table
Yeah.
transition by relaxing, so it's less performant.
Yeah, I mean, sure, you just do the transition table, you create the transition table once, but this actually takes a lot of time.
No, what I meant is like if you split it and do it on the UTF-8 level, on the byte level, you have more transitions. Like if you like working on the int level, on the UTF-8 code point level, then you have less transitions when you're decoding them.
Yeah.
Okay.
So.
Does anybody know if there's if anything outside of ASCII is used other than Universal Alpha?
I
And
don't know.
I think you can treat all of Universal Alpha as exactly the same character, as long as you can recover it later.
I think as far as figuring out a Lexer goes for D, the only things that you need to look out for as far as multi-byte characters, I think, are the paragraph separator and a few other things like that. Other than that, you can just, if you're iterating over the UTF-8, you can just say, well, keep going until we find an ASCII close quote, for example, if you're lexing a string or something like that.
Yeah.
Yeah.
At least that's the approach I took, is as far as I was concerned with my Lexer is that the only thing that's really important is finding where a token starts and where it stops. And basically all of those transitions are ASCII characters,
Yeah.
with the exception of a few Unicode whitespace characters.
Yes. So to summarize the point being, just do it by hand. It's not that difficult, and you can get a lot more performance out of it. And changing it afterwards isn't also that difficult if you take some care doing it correct in the first way. Yeah, but come back to the summary. Splitting the Lexer and Parser actually works. The code itself doesn't really look the same because you probably gonna write a function in the parser which basically is called next token, but does the token getting the tokens from the Lexer in a different way. Caching has great potential, considering how often you include files you included already, and how slow hard disks are, or even SSDs are in comparison to the RAM. Caching has some great potential, especially with line retrieves. This might just be interesting to look at. Multi-threaded semantic analysis is also a good approach, I think. If not for the speed part, then at least it will bring you cleaner code because you have one function doing one thing because it was meant to be run in a separate thread and you don't have some global state to pass some part of the other things. And coming to the D part of it really is the best part about D, what I found was the fast turnaround time. If I've used, for instance, C++, I probably would be compiling at this very moment to get my thesis done. And I had days where I had like cycles of crashing, fixing, building it and running it again like a couple times a minute even. I mean, this is one of the best things about D from like a coder standpoint of view. And also you have extremely expressive code if you do it correctly and think about what you have in the library and how to do it. You get a lot of stuff done in little code and you can even read it a week later or 2 weeks later, which is probably the most important part about it. And where D will be great is that at some point we're going to have extremely good documentation even on things like the grammar and on how stuff is meant to be working internally and how the semantic analysis are done and stuff. And what I hope is that we have a column instead of the dot dot. Yeah.
It's a column on its side.
Yeah, actually, I checked it and didn't really find a case where this would lead to some ambiguity in the grammar of the lexemes as well as the parser. I just liked it from Python, and this is just wonderful. And this just gave me the creeps and took a week to fix and get my head around. So.
Unicode have an ellipsis character?
Yeah, probably, but I don't know which keys I have to press on my keyboard to get this character, so this would even be a bit more problematic for some people. And what I also hope will be there someday are containers, because I missed them dearly while writing the compilers. So most of the code I was writing was creating containers for the set, for the map. I implemented even a hash table because I was confused on how the hash table stuff gets extended in the language itself to the dictionary, and yeah, and I really miss containers, and I think they will be a great addition to D, because they have great potential when you think about how ranges are already extremely beautiful, and if you have even containers which take ranges, this would be just great. I mean, yeah, but overall you can say D is extremely nice to work on as on alone, but also in a team. I had a smaller project run afterwards with some other people, and this was also nice. And you don't have to check headers that they are correct. And yeah, wonderful language, I have to say. And I think with Cruz. And probably most of you thought, who's Grace Hopper? It's her, Rear Admiral Grace Hopper, and she has a nice quote. And there you can find the source if you want to have a look at it. And you can also find my thesis under the last link if you want to get a bit more into it. And I think I'm done. Probably everybody's hungry right now, because next point on the schedule is lunch. Yeah?
Could you turn a slide back so I can count on your 3 points? So good documentation. There is a pull request running right now in deepprogramminlanguage.org from Sönke Ludwig, which is essentially gonna transform our documentation from 1 page per module to 1 page per entity, per function and class and structure. That's going to be a huge change. It's also going to allow community-created documentation, just in a PHP style. Regarding colon instead of ... I'm surprised it's creating so many problems to a parser. I don't know. We can talk. One alternative would be to disable the double syntax. That's 1 point is really 1.0.
Yeah, or just get rid of floating point. I mean, who needs this anyway?
Right. And there is a red-black tree in our containers library, but definitely there's more work to be done in that area. So points very well taken. I do have a question too, which is, okay, I know you're doing research, and I know what research code looks like. And, in your estimate, what would it take to take your research code and make it into industrial strength code for a real...
I think the first part would be documentation, because I have maybe 100 lines of documentation. This is basically just for disabling code. The second part, I would create the Lexer and Parser by hand, because the concept of running these in a separate thread is independent of the Parser and Lexer generator. So doing this by hand will probably have an extreme speed up, and you can just use the concept of multi-threading in this regard. And then, of course, you have to bind it to a backend and choose a reasonable backend and do all this kind of stuff, and then implement the semantic analysis, which I think will be the biggest chunk of code that had to be written.
Well, I just wondered to what extent does your project, to what extent is your project able to compile decode? How much did you get it working?
I was able to not compile because I haven't binded to a backend, but I was able to parse and generate the AST and the simple table to a degree of the language that was written in the grammar or into the modified grammar of the web page. So, for instance, I had basically I had a couple of test files which worked around the ambiguities in the grammar, and but to some extent, but not that much.
Do you think about like making it an interpreter just to test? I mean, run programs in some limited way?
Yeah, but then I pretty much ran out of time because I only had half a year. So
yeah, I definitely understand.
Yeah.
Is it really possible to do the semantic analysis in separate threads? We have so many inference. We have type inference. We have immutability inference.
Yeah,
you have to do some analysis and then you mutate syntax.
Yeah, this is like one of the assumptions you have to make. If the semantic analysis just looks at the data and checks if the stuff is correct, or if it modifies the code. So for instance, you can say that the inferring and the modifying is already done while creating the AST and symbol table, or is done in a separate stage in between this. Okay. So, but if you assume that you don't modify data, then it can be simply multiplexed on threads.
As far as the multi-threading and separating the Lexer and the parser goes, did you compare it to just applying the cache to the raw code and still having the Lexer parser tied together, but using another thread to load from disk?
No, I haven't.
And the other one, did you look at caching the processed code post semantic analysis?
I'm pretty sure the code was cached before the process was run, because I was, for creating the stats, I reran the process over and over again, like 1,000 times to get average results.
No. I'm thinking it's the saving after you said caching the original file, the tokens, the AST. But what about caching the stuff after you do like symbol lookup and possibly even code generation? And that
This would be another level. I mean, the last level you can think of where like the intermediate code or even the object file. I mean, there are more levels to come with it.
Regarding this point, it should actually be possible quite nicely in D, because we have like a module system which actually works and doesn't like include the files all over again. So it should be possible to actually dump the EST with semantic analysis run and just reuse it. Problem is just you have to like figure out more or less the connected components in your module dependency graph and just distribute this in some like useful way. But I think it's definitely a good idea.
Any more questions? Everybody's hungry. Yeah, he's rubbing his stomach. Good. Thanks.